Let's spend some time understanding the strangeness of quantum behavior. Now, this really starts to show whenever you start to break things down into the smallest possible building blocks of matter. So, namely, like electrons, photons, atoms, things like that. So, let's go through an example, right? Let's say I were to ask you, is light a particle or a wave, right? So let's say, oh, this is going to be a rough drawing. Let's say I've got a little sun here, right? And it's emitting light, and it's shining on our lovely, lovely scene, where we've got a nice little tree over here, and then you've got you, the stick figure observer, right? So light is going from the sun in this direction, reflecting off of the tree, and then back to you as the observer. Now, whatever it does this, is it acting as a particle or is it acting as a wave, right? Shouldn't it be one of those two things? Let's take the example. Let's suppose you have like a little camera right here, right? Look at that pretty tree. You want to take a photo of it. So the way that cameras work is something called the photoelectric effect, where a photon acts as a particle. It actually can reflect off of a little pixel well, so let's assume that that's one single pixel. Whenever a photon enters a pixel well, what'll happen is it'll kind of knock off an electron. So there will be a little electron that comes off of that metal and then gets recorded by the pixel well. And so what happens is cameras kind of just read in, hey, how many electrons are getting knocked off? And that kind of gives you a picture of your scene and the light intensity, right? So in this case, oh, cool, light is acting as a particle. However, let's think about another case, right? I need this to erase. Let's think about this in a different way. So this tree is going to be green, right? The reason that we know it's green is because we've measured it to be. We see the light reflecting off of this tree, and it's a specific wavelength, right? So light also operates as a wave with a specific wavelength, and that wavelength basically corresponds to the fact that it's green. So now you start to get into the weirdness of some quantum behavior, right? Because at its most fundamental level, we've now reached something called the wave-particle duality, where light acts both as a particle as it does a wave. So what I want to go through is chapter 1 of Feynman's lectures in physics, volume 3, where he kind of starts to introduce the concepts of quantum mechanics and particles and the weirdness in their behaviors. And so these figures are actually pulled straight from his textbook. So let's take this example, right? There's a lot going on here. So first of all, over here on the left, we have a gun with some beam, with some spread, right? There's some angle here where it is not very precise. It just kind of shoots off into a general direction. You can't aim it super well. And so what we want to do is there's this first wall right here that has 2 slits, 1 and 2. And there's this backstop that has a movable detector on here that basically allows us to say, okay, how many bullets are landing in each of these X positions on this wall, right? Because you can treat this wall as like an X all the way down. And so what we can do is as we're firing this gun, we can say, okay, if we were to close off this hole right here, hole number 2, and only take the bullets that are going through hole number 1, what's our probability that it's going to land across any of these positions in X? And so you see it kind of drawn out here where it's like, all right, well, it can reflect against this top part, and it can go down, and as all of these holes, all of these bullets can kind of end up in a small little region. So if we were to draw that out, we can say, okay, it's not really going to land down here. However, there's a bigger chance that it's going to land over here, and then smaller chance that it's going to land right there. We get a nice little graph right there. So now let's take the inverse case of like, all right, well, let's block this one. Well, what do we get? Well, we kind of just get the inverse of that, right? So we're going to have something that looks like this. And I'm doing a pretty bad job of drawing this, but I've painted over this. And so what we can do is we can say, okay, here are the curves that we're working with. P1 is the probability of it landing on any of these on this x-axis through hole number 1. And P2 is the probability of it landing on this x-axis through hole 2. And so now, how do we quantify the joint probability, right? Saying, okay, if I have both holes open, what's the probability density across this entire axis? Well, it's pretty simple. All you have to do is you have to just take the sum of the two of them. And so whenever we get the sum of the two of them, we get this little guy. So really, really nice graph. All right, this makes intuitive sense. So let's go ahead and move on to the next phase of this. And the next phase is like, all right, let's deal with waves. Waves are a little bit different, and this experiment is set up in a little bit of a different way. So let's say over here on the left, instead of a gun, you have a wave source. And this could be, imagine you have just a flat pool across this plane, and you have something that's kind of poking the water in a periodic manner such that it generates periodic waves. So if we were to, using the same walls, block off hole number 2, and instead our detector on this side, it's not measuring the probability density, but more so the wave amplitude or the wave height at a specific location. So let's say we were to block off hole 2. Well, the wave would diffract at this hole, and you would just kind of get new waves that would spread out from this, and they would look pretty normal. And same thing that would happen with this one, right? You just get waves that would just diffract from this hole, and you wouldn't get any interference pattern, you wouldn't get anything strange. So what we actually see from this is we actually see that we get these same exact curves, because you can treat this as like the wave amplitude. And so the way that we quantify wave amplitude is by doing the absolute value of the height squared. So in that case, right here, the intensity of the wave also correlated to, which is directly proportional to the energy of the wave, is equal to the height of the wave measured on this wall squared, the absolute value of the height of the wave squared. So what happens whenever we allow the wave to diffract through both holes? You may be able to see it on this, but we start to get an interference pattern. And this is something that I'm sure if you've messed around with water, you've seen interference where you'll get peaks within the wave. Instead of it being a nice gentle outward flow like this, you start to get peaks and waves. And so what happens is if you allow it to travel through both holes, you get a nice little, here we go. You get a really nice interference pattern like this. And so what you can see is the highest intensity is at the center. So you can see whenever it diffracts towards the center, you get the most amount of intensity or energy within the wave. And then it slowly decreases. But you get these peaks, and then you get these troughs that are very steep. And so the way that we quantify the intensity of a wave with interference is we actually sum the intensities of the two separate waves within the absolute value. And so this one is the absolute value of h1 plus h2 squared. And that gives us the energy of this wave function right here. Now, we've kind of delved into how do particles operate, how do waves operate. So now let's get into the strange wave-particle duality nature of electrons. The nice thing about electrons is they behave very, very similarly to photons. And so we can actually do experiments with electrons and start to analyze their behavior. So if we were to kind of revisit the first experiment with the gun and instead turn it into an electron gun, again with some beam spread, with some detector that is along this backstop, what we can do is we can measure, we could say the same thing that we did with the bullets, right? We can measure, hey, what is the probability density across this x-axis that I'm going to receive electrons, given that hole 2 is closed, or given that hole 1 is closed. So in this example, electrons are shot through this first wall and against this detector, and we see some particle-like behavior, right? This is exactly what you would expect in your probability density curves for a particle, right? This is the same thing that we got whenever we ran this experiment, but with the gun. So the logical conclusion you could say is, okay, my prediction for P12, which is when both holes are open, is P12 is going to equal P1 plus P2. That looks really nice. We expect that, right? So we would expect that we would see consistency in the behavior. We'd expect to see a curve like this. But what actually happens is we get an interference pattern. So this interference pattern occurs when both slits in the initial wall are open. So what we can't say is we cannot say that P12 is equal to P1 plus P2 for electrons. This is the weird thing with wave-particle duality, where at the quantum level, quantum components like electrons, like photons, behave like particles, but also like waves. And so you may say, well, why is that? Let's dive a little deeper. Let's see what's happening, right? Because if you're getting a wave interference here, then what you could say is you could say, okay, I don't know if the electron is going through either hole A or hole B. We could say that with the gun because it would end up through hole 1 or through hole 2. But with the waves, you could make that assumption. And so what we can do is we can actually set up a little light right behind here. I'm actually going to go to the next page for this. So let's set up a light source behind this wall. And what this light source allows us to do is it allows us to kind of quote unquote watch the electrons. So we know that electrons scatter light. And so when an electron passes through either hole 1 or hole 2, what we'll see is we'll see a flash on that side of the light source. And so we can kind of correlate and we can say, okay, so I can measure and make sure that electrons are going to behave like particles here. This is going to tell us if they actually truly do behave like particles. So with this light source right here, as we close one hole and we close the other and run our experiment exactly as before, what we see is we see P1 and P2, they operate as planned, right? These are these nice particle curves. And we're saying, hey, we're seeing these flashes on either side of the light, and it's correlating to the, it occurs whenever a particle goes through the hole. So now we can say, okay, so when I close one of these two holes, I know that a particle, that an electron is going through one of them. So now what we do is we open both holes and we say, okay, let's observe this with the interference pattern like we got in the last experiment and see what happens. Well, amazingly, we see the flashes. We see the flashes of light. And so we start to run the experiment. We pass the detector along and get our measurements, and something not super fun happens. What we find is that we get the joint probability of the particle curves. We lose the interference pattern when we start to observe the electrons. So somehow, the light source that we have in observing the electrons changed the behavior of them such that we lost all semblance of wave. So this actually results in us going back to our same particle one. We get P1 plus P2 to create this particle curve. So that's the weirdness of quantum components and quantum objects, is that whenever we introduce observation, we change the behavior of these objects. Now, something we could say here is we could hypothesize and say, okay, well, let's suppose that our light source is actually acting on our electrons in such a way that it kind of averages out our P12 curve right here. So what we could do is we could say, okay, well, we know that the momentum of light is equal to Planck's constant over the wavelength. So if we were to increase the wavelength, what we would do is we would drop our momentum and reduce the effect that light would have on this. So what we see is as we increase our wavelength, as we go from something like this, something like light, to getting bigger, I increase the amplitude here too, whoopsie, to getting even longer and longer wavelengths, the flashes that we get on either side of the light start to increase. They get brighter as the wavelength gets larger and as our momentum drops. And there comes a point in which the wavelength of our observation, or the wavelength of the light that we're emitting, is actually longer than the distance between the holes. And what happens at that point is that we get just one big flash. We can't tell which side it went through, and only at that point, when our wavelength is larger than the width of our two holes, do we start to get the interference pattern again. So that kind of introduces Heisenberg's uncertainty principle that goes into the balancing act between the positional measurement of an object and the wavelength that you're emitting and that you're trying to do your experiments with. I'd like to go into Heisenberg's uncertainty principle in a later video, but his principle essentially tells us that we cannot arrange the light in a way that tells us which hole the electron came through without disturbing our nice interference pattern. And so we cannot say that we know that an electron went through either hole 1 or hole 2 because of that principle.